Hi folks, this is Dr. Brown. Wanted to review a couple of slides we recently covered, and terms we need to be adding to our growing vocabulary as chemists would be atomic number, that's the number of protons, mass number, that's the number of protons plus neutrons, and the mass of the electrons is essentially zero. Electron actually has about 1/1837th of the mass of a proton or neutron, so it's basically disregarded. So the mass of an atom comes again from the total number of protons plus neutrons, and they weigh about the same. Another word to add to our vocabulary is isotope. And isotopes are atoms of the same element that have different numbers of neutrons, so they have different weights. You will see this designated in something like this shown here with a superscript 1 and H, which we looking from our periodic table, we know that's hydrogen, and a subscript 1. This tells us that our atomic number is 1, means we have 1 proton, and our mass number is 1. That means we have a total mass of 1. That means we have no neutrons, and the mass is, can be attributed only to protons in this particular atom. And these designations are atom specific, so each type of atom, even though it might be in hydrogen, might have a different mass number, and indeed some of them do, and those are called different isotopes. Okay, so if we have an atom like this, it has a lower subscript, a subscript 1 and a superscript 2. That means we have a mass number of 1, atomic number of 1, and that atomic number is always the number of protons defines the name. So every hydrogen, everywhere, anywhere, will always have only 1 proton. You can have a different number of neutrons, and those are called different isotopes, but hydrogens everywhere will only have 1 proton. And we have a couple different isotopes listed here. We have a traditional, or protium, which is the hydrogen that has 0 neutrons. We have deuterium, which is hydrogen that has 1 proton and 1 neutron. We have tritium, which is a hydrogen that has 1 proton and 2 neutrons. And again, all these hydrogens have 1 proton. Sometimes we'll see something like this. This is a little bit scooted over, but this subscript 1 again defines it as hydrogen. That's somewhat redundant. Superscript 2 means we're going to have 1 proton and 1 neutron, and again I get the number of neutrons by subtracting this number from that number. So that's where I got my 1 neutron. This atom, however, has a plus charge, and that plus charge says that we have an imbalance of electrons and protons. If I have a plus charge, that means I have a deficiency of 1 electron. So instead of having 1 electron, I have 0 electrons since I'm deficient 1. So whatever the charge is, that will indicate a deficiency if it's plus, or an abundance of electrons if it's negative. And again, a neutral hydrogen, in this case this hydrogen, which is the common name tritium, should have 1 electron because it has 1 proton. I know how many protons it has because I can pick this up as the atomic number. Okay. The periodic table conveys a lot of information, and pieces of information it conveys are the charge. This leftmost, the up and down list of elements are called a group. So this is a group, as is this is a group, and this is a group. So up and down designations are groups. Side to side are called periods. So this is a period, and this is a period. So side to side rows are called periods. The up and down rows are called groups. Some of the common names that we give to some of the elements are alkali metals. That's the leftmost group, and they're always plus 1. The next one is the alkaline earth metals, and that is not alkali earth metals, it's alkaline earth metals as shown here, and these are always going to be plus 2. This set of elements that are kind of dropped down here are called transition metals, and because of the complex nature of their outside electron shell, they can have a whole bunch of different possible oxidation states. An oxidation state is just the charge on the atom. So we will use either Roman numerals, and you need to know 1, 2, and 3, what the Roman numerals 1, 2, and 3 are, and that's I, 2 I's, and 3 I's, or learn the Latin names, right, like ferric and ferrous. And we'll generally shy away from the Latin names and generally go with the Roman numerals. Also in this periodic table we can see the number of protons. The periodic table that you'll be given will have the weights on it. These are the masses. This particular periodic table is very simplified. It does not have the atomic mass or atomic weight. It only has the atomic number, and the atomic number is the number of protons. So these are transition metals. These elements in this group are called halogens. They're always -1, and the rightmost group are called noble gases. They're very stable. They generally do not form compounds at all, and you can kind of think of them as having a zero charge. They will not form compounds. That's a little bit of a misnomer, but you could assume these form no charges or form no compounds. The halogens will always be a -1 charge. These next group, a bonus point might be earned if you knew those were chalcogens. These are chalcogens. Another bonus point might be earned on a test if you knew these were the coinage metals. The coinage metals are copper, silver, and gold. They've traditionally throughout history been seen as valuable metals and used for coins. Okay. We will also see the colors on the periodic table, which have nothing to do with the colors of the actual elements themselves, but these in the left part are green, and those are metals. Metals generally form cations, are generally good conductors of electricity and heat, are generally malleable, which means they can be hammered into a thin sheet. They're generally ductile, which means they can be pulled into a wire, and they have luster, which means they're shiny. So that's all these designated with green. The blue ones through here are generally called nonmetals, and they form anions, which are negatively charged ions, and they're insulators. The metalloids are the ones in the diagonal through here, and they've got some unusual properties. They behave somewhat as nonmetals and sometimes as metals, and some of the unusual properties are taken advantage of, and I think we've got a very important one hidden under here called silicon. Yeah, that's silicon right there, and that's a semiconductor. If these are conductors and these are non-conductors, these through here can be called semiconductors, and germanium and silicon are both important. Silicon is a semiconductor used in the computer industry a lot. So this, in a later chapter we'll talk about exactly why the configuration is as it is, but for right now we need to know alkali metals, alkaline earth metals, halogens, noble gases, and it'd be good to know these are the chalcogens and the coinage metals, and you need to know these are transition metals also. Okay, another piece of information you might want to brush up on is the way we name compounds. And this is a very abbreviated list of some of the rules that you must know, or some variation of them, to name inorganic compounds. And some of these include the fact that compounds and elements have a zero charge. That means that the cation total charge balances the anion total charge. Only ions have charges. So if something has a plus charge or a minus charge, it's going to be an ion. If you have a container of something like sodium chloride or lithium bromide or phosphorus pentoxide, those are going to be neutral compounds, so the total cations are going to equal the total anions. And we'll talk about that more in class. When naming compounds, the cation is on the left and the anion is on the right. The cation is positively charged, the anion is negatively charged. The leftmost group, the alkali metals, are always +1 charge. That's lithium, sodium, potassium are always +1, and almost always hydrogen is +1, although there's some instances where it can be -1, but we'll call it +1 for most of the uses that we'll have for it. The alkaline earth metals are in the second grouping. They're always +2 charged. The halogens, fluorine, chlorine, bromine, and iodine, when they're in compounds, they'll end in "ide." So we have fluoride, chloride, bromide, and iodide, and they always have a -1 charge. Some of the common ions we need to be comfortable with are ammonium, which is NH4+. That's a derivative of ammonia, which is down here, NH3. But you need to know that ammonium is +1, acetate is CH3COOH with a -1, oxide is O2 O -2, sulfide is S -2 or 2-. So these have 2 negative charges. The common acids we need to be comfortable knowing are sulfuric acid, H2SO4, phosphoric acid, H3PO4, and nitric acid, which is HNO3. These acids end in ic, and they're called ic acids, and the ic acids yield the 8 anions, and 8 is ATE, not EIGHT. And what this is trying to say is that sulfuric acid yields sulfate. Phosphoric acid leaves phosphate. Nitric acid yields nitrate. So the ic acids, sulfuric, phosphoric, nitric, yield sulfate, phosphate, and nitrate. And if you think about this and try to decrease the amount of stuff you've got to memorize, 2 hydrogens off here, 3 hydrogens off here, and 1 hydrogen off here would yield the correct ion. Sulfate has a -2 charge, phosphate has a -3 charge, and nitrate has a -1 charge, because the corresponding acids have a similar number of hydrogens associated with it. Other common anions you need to know are hydroxide, which is OH-, and carbonate, which is CO3 2-. It comes from carbonic acid. The other strong acids you need to be aware of are hydrochloric acid. You could call that hydrogen chloride, it's HCl. Hydrobromic acid is HBr. You could also call that hydrogen bromide. Common compounds that we, at this state in our level of sophistication in chemistry, we need to know are water, H2O, ammonia, NH3, and that it can be used to derive ammonium ions, but ammonia, which is in household cleaners or baby diapers, is NH3. Methane is CH4, that's also called natural gas. And table salt is NaCl, sodium chloride. Because of the fact that water is so prevalent in our universe, water is in rivers, ponds, falls out of the sky. Anyway, water is everywhere. So many compounds form agglomerates with waters in defined relationships, and those are called hydrates. If you have 1 water per molecule, it would be called a monohydrate. You need to know the prefixes mono, di, tri, tetra, penta, hexa, hepta, octa, nona, and deca to name the 1 through 10 hydrates. We look in our books to get the details on that. This is just a note to remind you that you need to know them. And it's generally written with the formula and then a big fat dot and then the number and then H2O. So sodium dihydrate would be NaCl, big fat dot, 2H2O. And more detail around that's in your book. If you hear the word oxidation state, that's the same as the charge or the oxidation number, and that's whether it could be +1, +2, -1, -2. We can know what it is by learning these handy-dandy rules or looking at our periodic table. Transition metals have many different possible oxidation states because of their complex electron orbitals that exist. So 2 conventions are used. One would be using Roman numerals, and you need to know what 1, 2, and 3 are in Roman numerals. That would cover most of what you've got. And, or also you could learn the Latin names like Ferrius, Ferric, Ferrus, but we'll be generally using the Roman numerals. It's a lot easier to understand. If you have a name where you have an ic and an us, like Ferric and Ferrus, or Stanic and Stanus for 10, the ic is always going to be more positive than the us. The OUS is the designation for us. Other facts that you need to know at this point are the facts that organic compounds always contain carbon, and they generally come from animal or plant matter like trees, oil, any kind of chemicals from coal or natural gas would always be organic chemicals. Medicines are generally organic chemicals, as are pesticides, herbicides, vitamins, and things. Inorganic chemicals are generally minerals. They have no carbon. So the big difference here is inorganics don't have carbon and organics do have carbon. Also, we need to know that acids give up hydrogens easily. They give up H+ or hydrogens because they have stable anions. And also acids taste bitter, but in no way is this an invitation to put anything in your mouth in the lab ever. But acids do taste bitter and they give up hydrogens easily. Hope this helps.